we are ready for the third talk. I was told that they were very glad there was an Italian session chair, so I wouldn't butcher Federico's name. Actually, Federico is gonna give a talk today about. So it's my pleasure to introduce Federico, who's gonna talk about some more LLM interesting stuff.
Thank you so much. Yeah, so my name is Federico, and I'm a former undergrad at Northeastern. I'm currently on leave working as a research scientist at Cursor. And this is my talk on knowledge transfer from high resource to low resource programming languages for Code LLMs. So what are LLMs anyway? They're actually in practice a combination of two models. One is a tokenizer, which takes in a string and produces a list of numbers called tokens. And from these strings, you can also take these tokens and get exactly the same string you just put in. The other model is a transformer, which takes in this list of tokens and produces a probability distribution of the most likely next token. So what people do is they just take the highest likely one and generate that and go in a loop. Both of these models are trained on corpuses of text, but the transformer model is a bit more special because it's trained on a very, very large data set, which typically spans most of the internet. And it's particularly trained on the objective of predicting the next token given the previous. So how do you specialize these models for code? Well, you just train them on all of GitHub. And so StarCoder is such an effort that did exactly this. It's an open source model that has been trained on a good chunk of GitHub of permissively licensed code. So this is your MIT and Apache repositories. And it comes in different sizes and it's trained on 80+ programming languages. The big issue with this is, as we know, GitHub data is heavily skewed towards popular languages. So the languages we care about, like R, OCaml, Racket, Lua, and Julia, are an extremely small proportion of this distribution. It doesn't even fit in the chart, right? So naturally, this makes LLMs excel at languages like Python, Java, and JavaScript, while being much worse on languages like Racket and OCaml. Even worse, if we look at sort of the benchmarks that have been published in academia for evaluating these models, they're all on Python, right? And so this kind of exacerbates the problem, as we cannot really quantify how good these models are on different languages. So what we did a couple years ago is we released MultiPLE, which solves this issue by offering a suite of transpilers for these Python benchmarks to our 20 target languages. And it's quite easy to add a new transpiler for your language if you feel like. In this work, particularly, we care about the smaller set of languages, which is Racket, Lua, OCaml, R, and Julia, and the OpenAI human eval evaluation set, which seems to be quite popular here as well. And so this is an example from human eval. We have seen some before from previous talks. You basically give this function signature with the doc string to the LLM produces an answer back, and you run this on this unit tests that are not shown to the LLM at generation time. And for the model to get the question correct, it has to pass all of the unit tests. And because of this setup, we actually don't need the function bodies. They are just there for reference. And MultiPLE exploits this fact, and you only need to translate the function signature, doc strings, and tests into the target language. And since the tests are mostly first-order values, this translation is quite tractable. And doing this for our languages, we can evaluate some of the models we care about, and we can see like a drastic difference in performance between Python and Racket and other languages as well. To give an example, the 15B model performs 3 times worse on Racket than it does on Python. And this is even worse for some of the lower resource languages like OCaml. So what can we do to make these models good at these languages? The first obvious attempt is, okay, we can just take the GitHub data we have for these languages and continue training the model, right? And so this is what we did with the StarCoder-based 1B model, but this barely moves the needle. So then what can we do? Like, this is literally all the data we have. Like, where else can we get this data other than GitHub? Well, what we do is we are going to generate some data. Because Starcoder is quite good at Python. So can we transfer this knowledge to other languages? And the idea is that we can transfer Python training data from a language X while preserving language X's idioms. And it's important that we don't use the transpilers themselves to do this, because typically transpilers produce code that looks quite unidiomatic despite working. So what we're going to do this is actually use the language model itself. And to do that, we first gather a data set of seed Python functions on which we can translate on. And we particularly get ones from the same training data set as the model. And then we filter them down to ones that have documentation, that type check, and we also remove benchmark contaminants to make our evaluation clean. And through this process, we filter down 22 million functions to 400,000. The second thing we do is we now generate tests for our Python code. And we do this for two reasons. Firstly, if we can generate tests that run on the Python code, then it probably means that we have a higher probability that that Python code on which the tests run on is higher quality. And the second reason is we can use this as an evaluation suite to test our translation later on. And the approach to do this is quite simple. We just use the model itself to generate the training suite, and we keep the test suite, and we keep only tests that pass on the Python function. So the assumption is that the Python function is correct. And we only keep Python seed examples that have reached over 90% line coverage. So we have some signal that also the test suites cover some amount of the code. And through this process, we end up with 130,000 Python examples with comprehensive tests. So then, this is the crux of our approach, which we call multi-PLT. And what we do is we start off with our Python seed functions, and we make them into prompts with our multi-PLE in the target language. And from this, we generate 50 solutions with the base model, and then we end up training on these solutions. But wait a minute. We just said that these models were terrible at producing OCaml, so now we're going to generate broken OCaml code and train on it. Like, who wants to use that model, right? So then what we do as well is we translate the tests with multi-PLE, and we execute all of these tests in the target language. And we only keep the solutions that actually pass the tests. And so by doing this, we end up with very small training data sets. So training is quick and can be done on consumer-grade GPUs. And we train different sizes of models. So we train 1B models, which can easily run on your laptop CPU. We train 15B models, which require some kind of GPUs, but are quite performant. And then we train state-of-the-art 34 and 70B models, which require multiple enterprise GPUs. And all of our data is released publicly. So these are our results on multi-PLE. We can see that we have a very large improvement in performance, which brings us much, much closer to Python. And here performance is measured by the amount of solutions that pass the unit tests that the model has produced. Another interesting result that we have that is quite unusual in these ML experiments is that we have actually generated this data with this 15B model, but then we end up training the larger models on the data produced by the 15B model, and they still improve, which is quite unusual and interesting. The other kind of question is, okay, we trained this model on data that was translated from Python. Does that mean that this model is just going to produce Python OCaml and Racket? Well, this is a very cherry-picked example, but in here we can see that the model actually ends up producing a more idiomatic code, where on the top is the base model, and on the bottom is the our fine-tuned model. And more empirically, what we can do is we can adapt the grading rubric from Northeastern's HDDP class, and we can grade some of these examples. And all of these examples here, both of the base models actually produce correct examples. Both of the models produce correct examples that pass the tests. So here we are just basing our grading on style. And we have some mixed results, but from here we can kind of conclude that multi-PLT does not degrade on idiomaticity. The other problem is, okay, we literally only trained on functions, right? So can the model truly only generate functions? And to test this we built an adversarial benchmark to see if the model lost the ability to attend to top-level context and external libraries. And so every problem in this benchmark needs a helper function, a data definition, or to use a library. And for every language, the model has to work with exactly the same problems. So we can kind of compare between languages as well. And also here we have some mixed results. So we can see that we may have overfit on OCaml, where for the 15B model it does a little bit worse. But for all other languages and models, it seems to do quite well. So after releasing our dataset, a few things happened. StarCoder 2 came out, and they incorporated multi-PLT in their pre-training dataset. And StarCoder 2 improves a lot upon StarCoder on low-resource languages, but we cannot obviously conclude that multi-PLT is the cause, that there were many pieces that went into StarCoder 2. After that, MetaLlama 3 used a very similar technique to ours to improve the model's performance for several programming languages, including low-resource ones. And they evaluate on multi-PLE as well. So to conclude, LLM-powered programming tools are in widespread use. And at Cursor, we see that significant amount of code is generated by the LLM itself. But the benefits are mostly found when working on high-resource languages. And so this feels like programmers that care about low-resource languages are being left behind. And there is no obvious solution to this problem, as there is very little data, and we kind of already used it all. And so methods like multi-PLT are trying to close the gap, but much more work is needed. Thank you. And before taking questions, I just want to say that both me and Arjun are hiring. So Arjun is hiring PhD students at Northeastern. And I'm looking for applied PL researchers and research engineers at Cursor to build the future of AI. Thank you so much.
Hi, thanks for the great talk. By the way, I really like Cursor AI. I mean, great products. So you mentioned about this not only function level generation and translation. I'm wondering, beyond this benchmark, how much promising do you see the current approach could scale up to like the whole repository rewriting, like the whole repository level translation? For example, we're translating C to Rust, right? Like, yes. How promising such kind of synthetic data combined with synthetic tasks as well to scale up to that level of complexity of problem? Yes,
so I'm aware that UC Berkeley is working on exactly this exact problem, where you do repository-wide translation, and then you train on this translation. It seems quite tractable. It's a lot of engineering work, but there is no reason why you could not do it for repository level, right? Mostly in our work, we had to be constrained to single functions, because at the time, these models were mostly good only at that. And in addition, we wanted to study multiple programming languages. And for each transpiler, there is a lot of work that goes into it, right?
Right. A quick follow-up. So how do you really model the dependencies like within the repositories?
That's right. So the idea that's currently spread around in the community is to utilize mocks, right? You mock away dependencies. Yes.
Hey, thank you so much for the talk.
Thank you.
I really like your results, but I'm a little confused as to what to take away from the talk, because at a high level, you're saying that if you have low resource languages and LLMs are not performing well on them, you just generate more data and fine tune them.
Sorry, could you say that again? Could you come a little closer?
At a high level, I'm not sure what to take away from your solution, because it feels like you're saying when LLMs don't perform well on a given language, the only solution is to just gather more data and train the LLM. And in some sense, that's cheating, because that doesn't remain a low resource language anymore when you have more data for the language.
Yeah.
So do you have any insights on what people should do when they don't have access to data?
So, like many ML experiments, we cannot make very large conclusions about why our thing works. But as you saw, our data sets are very small, but they make the model perform better. So one hypothesis on why that's true is because we are reusing the same Python data that the model has already seen, and we are transpiling it to the target language. Literally, the natural language is also the same. So our hypothesis is actually the model is not learning to do anything new when you train on this transfer data set. It's kind of reusing the same representations that it uses while writing Python in the target language. So I think that these approaches of transfer learning are way more promising than gathering more data. Like our data sets are super small. They are not even the close to the size of the subsets that we have trained on the stack, but they work, and the training on the stack doesn't. Does that answer your question? Thank you.
Thank you so much for the very nice talk. Just curious, have you tried grading the outputs of the existing code models when you first started collecting the?
Sorry, could you come a little closer?
Did you try to grade the outputs of existing code models using like the ones using your course when you started collecting data? I mean, you only did that afterward. After you only evaluated the outputs of your model using that grading scheme.
Oh,
right?
we also graded the base model.
Oh, okay.
Right. So in this graph, the bars with the line, that's our model. The solid bars, that's the base model. Yeah.
Okay. Okay, I missed that. Sorry.
Yeah. So one thing to take away from this graph is important is that here we only show the solutions that pass for both. In our fine-tuned models, there are more solutions that pass as well.
Thank you for the great talk.
Thank you.
One of the things I worry about in our sort of AI-driven future is, like, how are people going to adopt new programming languages, like no-resource programming languages? Do you think you could use this same technique to sort of automatically generate synthetic training data to help, like, on-ramp onto a new programming language?
Yes, I think that is necessary, because these code completion tools, I feel like they will become as necessary as syntax highlighting is today. Right. And so if your model cannot produce these programming languages, people are just not going to use your programming languages. They're going to write Python because you're just going to be faster at writing Python. Yeah. Right. So I feel like these techniques are actually just necessary because there is no code to bootstrap from. Right.
Yeah. Very cool. Thank you.
Thank you.
We still have time for some questions. I have a question. You want to go? I'll ask my question in the meantime, because. So what happened in old school machine learning, so the stuff from more than 3 years ago, is that people were getting really good at MNIST. MNIST was the data set, and then we thought models were getting better and better, but we found out that they were just getting very good at MNIST. They weren't getting better. So somebody then rewrote MNIST, and it turns out that the models weren't performing as well when you just did, and this led to all this work on distribution shift. I'm a bit worried that we are becoming very good at MBPP. And so it's not that the models are getting smarter, we are just getting good at mixing training and test data. So can you comment on that?
Yeah, well, we're going away from human eval and MBPP right now because just these models are becoming much, much smarter, and like the newest series of models literally saturate the benchmark. So the follow-up to this work would be doing it repository-wide, as somebody has commented. Yeah.
Oh, I was just going to ask how well this technique works with maybe different languages from different paradigms.
Oh yeah.
Like there's different.
Oh yeah.
Mental models. Even with the idiomatic, it's like, hey, the filter map reduce is going to be different than a bunch of for loops.
Yeah. That's a good question. So yeah, we tried that. So we did translation to Lua, and translation to Lua does better than translation to Racket and OCaml, but still, it's better than no translation, you know.
Let's thank the speaker again. That was a great talk.